Night combat is brutally unforgiving. On the modern battlefield, smoke, fog, and absolute darkness render standard RGB optical sensors completely blind. Relying on a single sensor in these degraded visual environments is a death sentence for an autonomous system. While long-wave infrared or thermal cameras can pierce through the veil of night by detecting heat emissivity, they severely lack depth perception, spatial resolution, and textural detail. Conversely, high-frequency millimeter-wave radar can easily penetrate dense atmospheric obscurance to deliver precise radial distance and Doppler velocity, but its output is a ghost town of sparse, noisy point clouds, highly susceptible to multipath reflections and electronic jamming. The ultimate solution to this perception crisis is Heterogeneous Sensor Fusion, a unified architecture that binds the semantic clarity of thermal imaging with the geometric invulnerability of radar. Welcome to the SWaP-C report. Today we are dissecting the perception engine of the future. We are tearing apart the tracking by detection paradigm, exposing the identity switch flaws of YOLO from a drone's perspective, and revealing the mathematical symphony of NOWA-MOT, the graph neural network that acts as YOLO's infallible memory. How do we teach an artificial intelligence to see in the dark? We deploy advanced edge AI models, specifically optimized versions of YOLO v8 and YOLO v11, running on high-performance compute modules like the NVIDIA Jetson AGX Orin, or the upcoming Jetson Thor, which boasts a staggering 2,070 teraflops of AI performance. In the tracking by detection paradigm, the tracker treats object detection and data association as two distinct, sequential tasks. YOLO serves as our primary perception engine, processing thermal frames frame by frame to generate 2D bounding boxes and class probabilities. But training these networks on military electro-optical and infrared datasets such as the FLIR thermal starter dataset exposes a brutal reality. Thermal imagery is plagued by heat blooming and thermal crossover, where the target's temperature merges with the ambient background, destroying sharp pixel edges and degrading gradient flow. To counter this, engineers physically modify the YOLO architecture by injecting convolutional block attention modules, or CBM, directly into the network's neck. CBM acts as a dual-dimensional feature calibrator. It sequentially applies channel attention to prioritize what feature maps contain critical infrared signatures, followed by spatial attention to pinpoint where the target is located, effectively suppressing background thermal noise. Despite these attention mechanisms, YOLO is functionally amnesic. It perfectly boxes objects in isolated frames, but it suffers catastrophic failure in the form of identity switches when occlusion occurs. From a drone's high-altitude perspective, targets frequently pass behind trees, structures, or even other targets. When a target is partially obscured, YOLO's confidence score plummets below the detection threshold, and the standard logic simply discards the bounding box. When the target reemerges, the tracker initiates it as a completely new entity. Enter NOWA-MOT, Neighbors Know Who We Are, a framework designed to serve as YOLO's infallible memory. The first line of the defense in NOWA-MOT is the low-confidence occlusion recovery module. Instead of blindly discarding YOLO's low-confidence bounding boxes, the LOR module actively salvages them to maintain trajectory continuity. It dynamically adjusts the confidence scores by calculating a highly specialized multi-Q similarity function. This function integrates standard intersection over union, spatial proximity constraints, and a novel metric known as Recovery IoU. Because an occluded object's bounding box shrinks unnaturally, Recovery IoU simulates a non-occluded state by mathematically expanding the dimensions of both the detection box and the Kalman Filters predicted trajectory box. The LOR module breathes life back into degraded thermal detections, elevating them into the high-priority matching pool. But salvaging 2D bounding boxes is only half the battle. To engage a target in physical space, we must build the bridge, heterogeneous data alignment. This is the heaviest engineering challenge in modern sensor fusion. How do you mathematically merge a flat, two-dimensional thermal pixel array with a volumetric, three-dimensional millimeter-wave radar point cloud? It requires flawless spatial and temporal synchronization. On board the UAV, a companion computer running the ROS-2 Humble middleware orchestrates this chaotic data traffic. To handle the immense bandwidth without choking the CPU, the system bypasses standard TCP/IP protocols. Instead, it leverages the data distribution service, specifically utilizing Cyclone DDS or Micro-XRCE-DDS to achieve zero-copy transport. The GPU handles the heavy lifting, allowing the Fusion bridge to operate under a ruthlessly strict sub-20 millisecond latency budget. To spatially align the data, the system relies on a rigorous projection matrix. Radar sensors output targets in polar coordinates. These are converted into a 3D body coordinate system via trigonometric mapping. Then the intrinsic camera matrix is multiplied against the extrinsic matrices. This calculation forces the 3D radar point to collapse perfectly onto the 2D plane of the thermal camera, giving each YOLO bounding box an exact, verifiable depth and velocity profile. But what happens when the target is entirely engulfed in artificial smoke? The thermal camera is blind, YOLO sees nothing, yet the millimeter wave radar continues to ping the moving chassis. Here, advanced control theory takes over. We rely on the extended Kalman filter, or its more advanced variant, the Unscented Kalman filter, to maintain the target's state estimation. Real-world targets do not move in perfect straight lines. They maneuver evasively. Therefore, the tracking algorithm relies on nonlinear motion models, such as the constant turn rate and velocity model. The filter continuously updates a multidimensional state vector comprising the target's position, heading angle, velocity, and yaw rate. Because these equations are highly nonlinear, the extended Kalman filter utilizes Jacobian matrices to linearize the predictions. Alternatively, the unscented Kalman filter bypasses linearization entirely, using a deterministic sampling of sigma points propagated through the unscented transform to capture the true mean and covariance of the target's trajectory with supreme accuracy. Yet, the ultimate challenge remains. How do we associate these radar-guided mathematical predictions with the chaotic, returning visual detections from YOLO once the smoke clears? Historically, systems relied on the Hungarian algorithm to match tracks to detections based on simple geometric overlap. But in dense, highly occluded combat scenarios, geometry is not enough. This is where NOWA-MOT introduces its most devastating weapon, the graph cross-attention, or GCA module. The GCA module fundamentally alters the data association paradigm. It constructs two separate entities, a trajectory graph composed of active historical tracks and a detection graph built from the current frame's YOLO outputs. Rather than looking at objects in isolation, GCA employs multi-head graph cross-attention. It extracts deep appearance features using an OSNet backbone and concatenates them with topological spatial features. The cross-attention mechanism then acts as a neural bridge, aggressively propagating rich contextual information between the trajectory nodes and the detection nodes. By executing a dual softmax operation, it enforces both row and column-wise competition, generating highly discriminative feature representations that resist confusion even when targets cross paths. Finally, to resolve the most severe, prolonged ambiguities, NOWA-MOT acts as a predictive physics engine through its match neighbor guidance module. The M&G module is built on a simple but profound combat truth. Targets traveling in a group exhibit coherent motion patterns. When a target is hopelessly unmatched or hidden, the M&G module refuses to guess blindly. Instead, it anchors onto the reliably matched YOLO detections surrounding the hidden object. By enforcing strict distance, velocity, and directional constraints, M&G selects the optimal neighboring trajectories. It then constructs a star-shaped topological feature graph, placing the unmatched trajectory at the center and its stable neighbors at the points. By aggregating the motion and appearance features of the visible pack, M&G calculates a topological distance metric that accurately infers the identity and location of the hidden object based entirely on the geometry of its peers. It guides the final Hungarian matching matrix, not with raw guesses, but with context-aware structural certainty. From the dynamic salvaging of low-confidence thermal artifacts to the complex graph-based topological reasoning of target clusters, The integration of thermal YOLO and NOWA-MOT represents the terrifying perfection of the multimodal autonomous night hunter drone. It is a system that does not just see the battlefield. It understands it, remembers it, and predicts it entirely at the edge in a fraction of a second. If you want to stay on the bleeding edge of aerospace, edge computing, and defense engineering, hit that subscribe button. This is the SWaP-C report. We will see you in the next deep dive.